Chapter 9, which consists of 6 modules, is about higher order differential equations. In module 1 is the most introductory part, where we will define autonomous and non-autonomous system, how an nth order differential equation can be converted into a n first order linear differential equation, and about the linear independence and dependence of the solution. In this chapter, we will study the following system of first order equation of the form dx1 dt is equal to f1, which is a function of t x1 x2 dot dot xn, dx2 dt equal to some function f2, dxn dt some function fn, which is again the function of t x1 x2 dot dot xn, where f1, f2, fn are n given functions defined in some region D of n plus 1 dimensional Euclidean space, and xi's 1, 2 dot dot n are n unknown functions of a single independent variable t. Now, systems of differential equation arise quite frequently in dynamical systems. For example, we have pendulum problem, coupled harmonic oscillators, population models, mixing problems, control problems, and many more problems which are studied using a system of differential equations. A solution of the given system 1, which was defined in the previous slide, is a set of n functions x1, x2 dot dot xn, where t belongs to I is an interval which is need to be found, such that dxi dt from I1 to n exist for each t belongs to I. The point t x1 x2 dot dot xn remains in D for each t in capital I, and dxi dt is equal to fi t x1 x2 xn for I equal to 1, 2 dot dot n for each t belongs to I. To find a particular solution x1t, x2t dot dot xnt, we often choose a fixed point t equal to t0 and assign appropriate values to x1t, x2t dot dot xnt at t equal to t0, and we write x1 t0 is equal to x10, x2 t0 equal to x20 dot dot xn t0 equal to xn0, given by equation 2. Most of the times, the fixed point and the corresponding values of xit are given along with the physical system. Equation 1 together with the initial condition 2 is known as an initial value problem. A solution of the initial value problem is a solution x1t, x2t dot dot xnt of 1 satisfying the initial conditions 2. Now, in this example, it can be easily verified that x1t is equal to e to the power t into 1 plus t and x2t equal to e to the power t forms a set of initial value problem. Now, you can easily prove that by substituting x1t and x2t in this differential equation to see they are satisfying this particular initial value problem. For example, it can be easily verified that if you put x1t equal to e to the power t into 1 plus t in this differential equation, the first one is going to give you the differentiation of this, which is e to the power t plus 1 plus t into e to the power t, and if you substitute that here x1 and x2, both the left hand side and the right hand side will be the same. Also, if you put t equal to 0 here, this is going to give you the value 1, which is satisfied by this particular expression. The same thing, it can be checked that if you differentiate x to t, it is going to give you e to the power t, which is x2 t, and hence it is satisfying this particular differential equation, and also x2 0, if you substitute t equal to 0 here, it is going to give you e to the power 0, which is 1, and hence it can be easily verified that both x1 t and x2 t forms the solution set of this initial value problem. Now, the wide applicability of the system of differential equation is due to the fact that every single nth order differential equation of dependent variable y in a single independent variable t can be represented by a system of n first order equations of the variables x1 t equal to y, x2 t equal to dy dt, xn t is equal to dn minus 1 y by dt n minus 1. Consider the following initial value problem: dny dtn is equal to f t y y dash y n minus 1, that is n minus 1th derivative, with the initial conditions y t 0 equal to y 0, y dash t 0 equal to y 1 y n t 0 equal to y n minus 1. Now, this nth order differential equation we can convert into a system of first order differential equation in the following manner. You just substitute x1 t equal to y, x2 t equal to dy dt xn t is equal to the n minus 1th derivative of y, that is dn minus y dt n minus 1, and then we will get dx1 dt is equal to x2, dx2 dt is equal to f3, like that dxn dt is equal to f some function of t x1 x2 xn, and moreover the functions x1 x2 xn satisfy the initial conditions x1 0 equal to y 0, x2 0 equal to y 1 xn 0 equal to y n minus 1. If each of the functions f1 f2 fn in equation 1 is a linear function of the dependent variables x1 x2 xn, then the system of equations is said to be a linear system, otherwise it is called a nonlinear system. The most general system of n first order linear differential equation will have the form given by equation 3, which is dx1 dt equal to a11 x1 plus a12 x2 plus a1n xn plus some f1 t, like that dxn dt is equal to an1 x1 plus an2 x2 plus plus ann xn plus some fn t. If each of the functions f1 f2 fn is identically 0, then the system 3 is said to be a homogeneous system, otherwise it is called a non-homogeneous system. Let capital A be a n cross n matrix with elements aij, so we are function of t, and let ft and x be vectors with components f1 f2 fn and x1 x2 xn respectively. Then we can write 3 in the much simpler form: dx dt is equal to atx plus ft, given by equation number 4, where at is a matrix a11 a12 a1n a21 a22 a2n an1 an2 ann. All the aij's are function of t. X is the vector x1 x2 xn and ft is the vector f1 f2 fn. Moreover, if x1 t x2 t xn t satisfy the initial conditions x1 t0 is equal to x1 0, x2 t0 equal to x2 0 dot dot xn t0 equal to xn 0, then xt satisfies the initial value problem dx dt is equal to at into x plus ft x t0 equal to x0, where x0 is the vector x10 x20 dot dot xn0 and ft is another n component vector f1 f2 dot dot fn. If at is equivalent to A, where A is a constant matrix, then the system 4 is called a autonomous system of linear equations. Otherwise, the system is called a non-autonomous system of linear equations. Given the basic definition of autonomous and non-autonomous system, we now move into the homogeneous systems, some basic definition of the norms, and the linear dependence and independence of the solution of the higher order differential equations. We now consider the linear system of differential equations dx dt is equal to atx plus ft, where x is equal to n x1 x2 dot dot xn, A is the matrix a11 a12 dot dot a1n dot dot an1 an2 dot dot ann, where all the aij's are function of t, and capital Ft is equal to f1 f2 dot dot fn. To initiate the study of linear homogeneous system, we have to put Ft is equal to 0, that is, there is no external force Ft in equation 5. We first make sure that the system has a solution. So, first we state the existence and uniqueness theorem without proof. The proof of the following theorem can be given in a similar manner as we did in the proof of Picard's theorem in previous chapters. The only noticeable change is the change of the modulus function with a suitable norm function. We may define a norm of a matrix denoted by norm A in several ways, and all the norms are equivalent to each other. The most common norms are norm 1 and norm 2 of the matrix A, which we defined as norm A, the first one, is equal to summation ij equal to 1 to n mod of aij, and the second norm of the matrix A is equal to square root of summation ij equal to 1 to n mod of aij square. As all the norms are equivalent, we will drop the subscript, this 1 and 2, and denote the norm of the matrix by norm A only. It can be easily checked that the matrix norm satisfies the following basic properties. The first one, norm of A plus B is less or equal to norm A plus norm B. Number 2, norm of AB is less or equal to norm of A into norm of B. And number 3, norm of A into small b is less or equal to norm of A into norm of small b. For all matrices A, B of complex real numbers of order n and the vectors B n cross 1 is equal to Bi, where norm of B is equal to summation I equal to 1 to n mod of Bi. Consider the following linear homogeneous system dx dt is equal to atx, x is equal to from 1 to dot dot xn, and at is equal to a11 a12 dot dot a1n, an1 an2 dot dot ann, all aij's are function of t. The uniqueness and existence theorem says if at, ft are continuous on an interval A less or equal to T less or equal to B if T0 belongs to the closed interval a b, and if norm of x0 is a finite number, then there exists one and only one solution of the differential equation 5 with initial condition x t0 equal to x0 on the closed interval a b. For the autonomous system, the following existence and uniqueness theorem are stated as follows. There exists one and only one solution of the initial value problem dx dt is equal to ax, where x t0 equal to x0, which is equal to x10, x20 dot dot xn0. Moreover, this solution exists for all t between minus infinity to plus infinity. Once we know that a solution exists, we want to know the structure of solutions of the linear system. So, we start with the linear homogeneous system x dash is equal to ATX. Here we assume that the matrix AT of n order is a continuous matrix over the closed interval I, which is equal to AB. Since the system 6 is a linear system, so we can easily check that if x t and y t are any two solution of 4, then C t x t is a solution where C is a constant and x t plus y t is also a solution. Let capital V denotes the vector space of all the solutions of the linear system 6, and we want to know the dimension of V and the basis of V. Next, we define linearly dependent of the vectors. A set of vectors u1, u2 dot dot um is linearly dependent if there exist scalars ci's I is equal to 1, 2 dot dot m, not all zeros, such that the linear combination summation I equal to 1 to m ci ui equal to 0. A set of vectors u1, u2 dot dot um is linearly independent if it is not linearly dependent. The next theorem states, if the matrix A, which is of order n, is continuous on an interval I, then on the interval I the solutions of the system x dash is equal to ATX forms a vector space of dimension n. To show that the dimension of vector space is n, we have to construct a basis for vector space consisting of n linearly independent vectors in V, that is, of n linearly independent solutions of 8 on the interval I. Let T0 be any point of I and let E1, E2 dot dot En be any n linearly independent points in Euclidean space En. Then by existence and uniqueness theorem, the system 8 possesses n solutions, namely Z1, Z2 dot dot Zn, each of which exists on the entire interval I, and each solution satisfies the initial condition Z z T0 equal to E j, where j equal to 1, 2 dot dot n, given by equation 9. We first show that the solutions Z1, Z2 dot dot Zn are linearly independent on I. Suppose they are not, then there exist constants a1, a2 dot dot an, not all zeros, such that a1 z1 plus a2 z2 plus dot dot a n z n is equal to 0 for all t belongs to I. In particular, putting t equal to t0 and using the initial conditions, we have a1 e1 plus a2 e2 plus dot dot a n e n is equal to 0, which is impossible unless a1 a2 dot dot a n are all zeros, and hence it contradicts the assumed linear independence of e1 e2 dot dot e n. Now, we show that these n linearly independent solutions of 8 span the vector space capital V. We compute the value of the solution psi at t0 and let psi t0 equal to E. Since the constant vectors e1, e2 dot dot en are linearly independent in the Euclidean n space En, they form a basis for En, and there exist unique constants C1, C2 dot dot Cn such that the constant vector E can be written as E equal to C1 E1 plus C2 E2 plus dot dot plus Cn En. Now, consider the vector zt is equal to C1 Z1 plus C2 Z2 plus dot dot Cn Zn. Clearly, zt is a solution of 8 on the interval I. Moreover, the initial value of z is zt0 is equal to C1 E1 plus C2 E2 plus dot dot Cn En is equal to E. Therefore, zt and psi t are both solutions of 8 on the interval I with zt0 is equal to psi t0 is equal to E. Therefore, by uniqueness part of existence and uniqueness theorem, zt is equal to psi t for every t belongs to I, and the solution is expressed as the unique linear combination psi t is equal to C1 Z1 plus C2 Z2 plus dot dot plus Cn Zn for every t on I. In this theorem, we have a test for linear independence. Let x1 x2 dot dot xn be k solutions of the differential equation dx dt is equal to Ax. We select a convenient t0, then x1 x2 dot dot xn are linear independent solutions if and only if x1 t0, x2 t0 dot dot xn t0 are linearly independent vectors in Rn. The proof: suppose that x1, x2, x3 dot dot xn are linearly independent solutions of 11. Then there exist constants C1, C2 dot dot Cn, not all 0, such that C1 x1 plus C2 x2 plus dot dot Cn xn is equal to 0. Evaluating this equation at t equal to t0 gives C1 x1 t0 plus C2 x2 t0 plus dot dot plus Cn xn t0 is equal to 0. Hence, x1 t0, x2 t0 dot dot xn t0 are linearly independent vectors in Rn. Conversely, suppose the values of x1, x2 dot dot xn at some time t0 are linear dependent vectors in Rn, then there exist constants C1, C2 dot dot Cn, not all 0, such that C1 x1 t0 plus C2 x2 t0 plus dot dot Cn xn t0 is equal to 0 vector. With this choice of constants C1, C2 dot dot Cn, we construct the vector valued function phi t is equal to C1 x1 t plus C2 x2 t plus dot dot plus Cn xn t. This function satisfies equation 11 since it is a linear combination of solutions. Moreover, phi t0 equal to 0, x t0 is a solution of 11 satisfying the initial condition x t0 equal to 0. Hence, by theorem 0.2, phi t is equal to C1 x1 plus C2 x2 plus dot dot plus Cn xn is equal to 0 for all t. This implies that x1, x2 dot dot xn are linearly dependent solutions. We consider the example with this system of differential equation dx1 dt is equal to x2, dx2 dt is equal to minus x1 minus 2x2, which can be put in the matrix form dx dt is equal to 0 1 minus 1 minus 2 into x, where x is equal to x1 x2. This system of equation is also equivalent to a single second order equation of the form d2y dt square plus 2 dy dt plus y is equal to 0. So, all we have to do is to eliminate x1 and x2 from here by setting x1 is equal to y and x2 is equal to dy dt, and you will get this equation 13. Now, it can be easily shown that y1 is equal to e to the power minus t and y2 is equal to t e to the power minus t are two solutions of 13. As you can see from here, the auxiliary equation is m square plus 2m plus 1 equal to 0, which gives m equal to minus 1 and minus 1, the repeated roots. Hence, its solution are e to the power minus t and t e to the power minus t. And since these e to the power minus t and t e to the power minus t are the two solutions of 13, it can be seen that x1 t is equal to e to the power minus t and minus e to the power minus t, and x2 t is equal to t e to the power minus t and 1 minus t e to the power minus t are the two solutions of 12. Also observe that x10 and x20 are linearly independent vectors in R2. Consequently, by theorem 0.4, x10 and x20 are linearly independent solutions of 12, and every solution xt of 12 can be written in the form xt is equal to x1t x2t, which is equal to C1 times x1t plus C2 times x2t, which is equal to C1 plus C2t into e to the power minus t and C2 minus C1 minus C2t into e to the power minus t, where C1 and C2 are arbitrary constants. In this module, we have given a basic definition, namely the autonomous and the non-autonomous system, the homogeneous and non-homogeneous equation, the linear dependence and linear independence of the solutions. In the next module, we will look into some higher aspects of the system of differential equations of higher order. Thank you.